So you may have a CNN, which is very, very powerfully trained, basically maybe on transfer learning done on ImageNet on very large sequence of images. Then the output of the intermediate model or the fixed length vector, you could pass it to an LSTM to generate language. So here, for example, you could have the image source, which is a classical image of a vegetable mart outside open market. So you have a output here which says a group of people shopping at an outdoor market. Similarly, there are many vegetables at the fruit stand. So these are things which it is learned from having trained a lot of original vectors being derived from text, which it is trying to reverse engineer and understanding text equivalent of the encodings which it has learned from the images. So this is one example. Another example, as I have already indicated, this is known as parallel corpus based sentence aligned machine translation, broadly coming under the area of what is known as neural machine translation. So what happens is, if you have a original source language sentences and they are mapped to target sentences in the target, then you learn the encoder decoder architectures from these mappings and use it when it comes to actually predicting the translation output of given a source sentence. And I want to actually present the historical importance of this slide. Till recently, till about 3 to 4 years back, machine translation in the natural language and computational linguistics field was considered the forte or the strong point of computational linguists, who were very good in language, and they were developing custom language models, grammar models for each language, and using those custom language models, they were trying to use domain specific rules to translate from source language sentence to a target sentence. For example, in Hindi or Sanskrit, so Hindi to Telugu translation, they were using notions of Prakrit grammar, which was the basis of the Sanskrit. Similarly, in other universal languages, they were developing language models corresponding to each languages. But there, the benefit of the domain knowledge of the linguist was very important. That would give how effective the translation was in terms of, they have something called as Bloom's quotient, which is basically looking at how good the translation is for a given corpus. And lo and behold, about 3 years back, Google's neural machine translation based on encoder-decoder architecture, which is purely a statistical LSTM encoder-decoder model developed based on the input sentences and output sentences given to Google as part of its translation service, and it having perfected the encoder-decoder architecture, it has started to give much better Bloom score for translations than even the best of the best conventional language models. So today, the world of machine translation in AI and NLP and computational linguistics has practically adopted neural machine translation as the technology as compared to conventional domain-specific language models. So such is the power of encoder-decoder architecture models today. And if you can see this, this is nothing but statistical approach. There is no language grammar which it is learning. It's purely learning the relationship between the target sentences and the input sentences. And such is the kind of power of encoder decoder architectures and how it has shaken the world of what we otherwise used to call as the domain of computational linguists or language experts in the form of machine translation. So neural machine translation is a very, very powerful use case for creating a target application for such encoder decoder architectures.